Hello everyone and welcome back. So, if you have followed my previous video, you might know that we made a CNN model. We actually trained a CNN model for a horse and human dataset that was generated by CGI. And when we ran it, we found that the training accuracy was more than the validation accuracy, means the model was overfitting. And one solution that we found was to add more images. But we found that sometimes it's very difficult to find more images. So here's the solution that we are going to talk about known as image augmentation. So let's read ahead. In previous section, you built a horse or human classifier model that was trained on a relatively small dataset. As a result, you soon began to hit problems classifying some previously unseen images, such as the miscategorization of a woman as a horse, because the training set didn't include any of images of people in that pose. One way to deal with such problems is with image augmentation. The idea behind this technique is that as TensorFlow is loading your data, it can create additional new data by amending what it has using number of transforms. So what we are going to do basically in image augmentation is that while the TensorFlow is loading your data, it can simultaneously create additional new data. So we have the data that we downloaded, but TensorFlow on the back end can also create additional new data by amending what it has and a number of transforms. And we'll see what kind of transforms TensorFlow can do in a while. For example, take a look at figure 3-11. While there is nothing in the dataset that looks like the woman on the right, the image on the left is somewhat similar. So, these are called dataset similarities. So, the woman on the right is somewhat similar to the woman on the left. So, you can see both have kind of similar posture, but the left one is zoomed out while the right one is zoomed in. If you could, for example, zoom into the image on the left as you are training, as shown in figure 3-12, you would increase the chances of model being able to correctly classify the image on the right as a person. So what he's saying here is that if we zoom on the image on the left, it will be kind of same as the image on the right, and there will be the probability of the model classifying the left zoomed in image as a human or as a person would be more. So here you can see. In similar way, you can broaden the training set with a variety of other transformations, including rotation, shifting horizontally, shifting vertically, shearing, zooming, flipping. Because you've been using image data generator to load the images, you've seen it to do transform already when it normalized the images like this. So in the previous code, we have already seen how we used image data generator to rescale our image, or basically I would say to normalize our image by 255. The other transformations that it can make are, for example, let's see this code here. So it's rescaling as it is. Then there is a rotation range of 40, width shift range of 0.2, height shift range of 0.2, shear range of 0.2, zoom range of 0.2, horizontal flip equals true, and fill mode equals nearest. So let's just understand this one by one. Here, as well as rescaling the image to normalize it, you're also doing the following. So what we are actually doing in the code, we'll understand now. So first, rotating each image randomly up to 40 degrees left to right. So left or right. So what we are doing here, the kind of transformation that we are applying is that rotation range equals 40 means that the image will be randomly rotated 40 degrees either left or 40 degrees either right. Next, translating the image up to 20% vertically or horizontally. So it's translating the image to 20% width in the width or in the height, that is horizontally or vertically. Sharing the image by up to 20%, zooming the image up to 20%, then random flipping the image horizontally or vertically. As we have already mentioned, horizontal flip equals true, as you can see on the top line of the code. Then filling in any missing pixels after a move or shared with nearest neighbors. So we are filling the fill mode equals nearest means filling in any missing pixels after a move or share with nearest neighbors. Next it says when you retrain with these parameters, one of the first things you'll notice is that training takes longer because all the images processing. So the training will take more time than the previous time. Also, your model's accuracy may not be as high as it was previously because previously it was overfitting to a largely uniform set of data. So previously the data was largely uniform. That means there was no such rotation, there was no such horizontal or vertical flips and all those kind of transformation that we have applied. It was not there earlier. In my case, when training with these augmentations, my accuracy went down from 99% to 85% after 15 epochs, with validation slightly higher at 89%. So this indicates that the model is underfitting slightly, so the parameters could be tweaked a bit. So what happened here is that the training accuracy went down from 99% to 85% because of the augmentations that we have applied. But at the same time, the validation went up from 88% to 89%. So this indicates that model is slightly underfitting. What about the image from figure 3-9 that it is misclassified earlier? This time it gets it right. Thanks to image augmentations, the training set now has sufficient coverage for the model to understand that this particular image is a human too. This is just a single data point and may not be representative of the results for real data, but it's a small step in the right direction. So as you can see, for the image they have added that name is beautiful 127 something .jpg and it classifies it as a human. So certainly it was the image of a girl. As you see, even with a relatively small data set like horses or humans, you can start to build a pretty decent classifier. With larger data sets, you could take this further. Another technique to improve the model is to use features that were already learned elsewhere. So what he is saying is that we can also use models who are already trained and use them elsewhere for our personal or different kind of data than they were trained on. Many researchers with massive resources like millions of images and huge models that have been trained on thousands of classes have shared their models, and using a concept called transfer learning, you can use the features those models learned and apply them to your data. We'll explore that next. So before we head on to transfer learning, let's give a trial to image augmentation that we have certainly read right now, and we'll look at the code and what kind of changes happen in that code we'll understand. Welcome back. So, for your convenience, I've already ran this whole notebook once again and I've also applied the image augmentation. So, now I am going to show you how the image augmentation is different from that we have done before. So we as usual are getting our training files, and here is our training data, and we are just rescaling it and applying all sorts of image augmentation that we have read about in the book. Then we have applied here and found that there are 1027 images belonging to two classes, and then we have defined our model.summary. Then we compiled our model, fit our model, and we got an accuracy of 96% in the end. And for the same, for validation images, we have done the same, that this kind of image augmentation we have applied that we have already read. So let's see that what kind of validation accuracy we've got is that the validation accuracy has turned out to be around 62% in the end. So it's actually varying from 82, 87, 75 to finally 62. So let's just take a range out of that. And when I tested few of the images, as you can see, I have uploaded two images of girls and two images of horses, and this is the outcome that I got. So it clearly classified girls as human, but it misclassified horse as a human as well. So it hasn't done a great job at classifying horses. So here is the final result, that before image augmentation, the training accuracy was about 98%, while the validation accuracy was about 80%. But after applying image augmentation, the training accuracy was decreased from 98% to a range of 93 to 96%. That's still decent, but it has clearly misclassified horses as humans. So we would not say that it generalized so well. But the accuracy for validation has surely increased by 2%, that's 82%, and the model is clearly underfitting. So we have seen that image augmentation hasn't helped us that bit, and surely, as we have read in the theory, we need to tweak the parameters here and there a bit, but we'll understand how all these problems can be overcome by using transfer learning in the next thing. So all this code will be available on GitHub, and you surely can test it out and run it for yourself, check with different images of humans and horses, and check out how your model performs on that.